said, and I practice mainly in Boca Raton, but I also practice in the Cayman Islands, which is about an hour's plane ride from my home here. We're going to talk about a lot of things today, but there's a lot of science, and there's going to be a lot of things you've heard of. There's going to be a lot of things you haven't heard of. Like Jim said, you know, I try and pride myself on sort of being ahead of the curve a bit, okay? So here's some of the things that I am working on. Pure Excel. Some of you actually know about that. You may buy things from us, etc. But need about that. All right, so let's get into the nitty gritty. Now, you know, this is a very important slide, and I have in yellow right here. Any attempt to analyze a cell basically alters its nature. So what I want you to realize is when you start looking at a study, and it's an in vitro study, it may not hold true, because when you take a stem cell or other regenerative cell out of its environment, it may do something totally different than it would do in vivo. So just keep that in mind, that you can't always translate one thing to another. Okay, so the other thing we need to know about some basics is what I call the crimes of cellular communication. We have autocrine, where the cell acts on itself. We have juxtacrine, where it can go in close contact. We have paracrine, which is how a lot of stem cells, PRP and things like that kind of work. You know, local cells work on other local cells. And then we have the endocrine system, which is, you know, a far distant way of doing things. Now, integrins are basically the transmembrane glycoproteins that help with the attachment of cells to the extracellular matrix. So just kind of keep that in mind. You know, we're going to briefly, now one thing I'm going to tell you, I told Jim that I'm going to make my slides available to all of you. So this way you can go and look at these at your leisure. And certainly you can email me and say, I have a question about this. I have an opinion. What do you think about this? Can you give me an idea? I'm more than happy to help you. So first I want to talk about PRP. That's what I started working with about 15 or 16 years ago, okay? Now, interestingly enough, you know, there's an unexpected role of the platelets, okay? Basically, platelets are involved in the immune response. We sort of thought about that. Neutrophils scan for activated platelets, okay? So if they see a platelet's activated, neutrophils get attracted to that area. And I've given you some of the literature. I'm going to give you literature throughout the whole talk. So basically, when we look at platelets, we know, and this is sort of basic stuff, but I just want to go over it a bit. We have the alpha granules, the dense granules, and the liposomes. Now, basically, the alpha granules are the important ones, and when we really look at things, they're all important, but this is probably where we find most of the things we're interested in. Various growth factors, they cause growth, angiogenesis, things like that. You have IGF-1, VEGF, things like that. Okay, so basically, these are growth factors in platelets. Now, what I call basically these growth factors, I'm going to show you right here. This is what I call the growth factors. It's the body's cell phone system. It's how one cell can communicate with another, okay? And again, these are, again, another slide that shows you the various components of a PRP. All different kind of things, alpha-2 macroglobulin, angiopoietin, all sorts of things that we find there, okay? Now, I was talking to Jim before we started the talk. I said, you know, Jim, I'm going to talk a little bit about sort of exosomes that come from platelets. Well, believe it or not, there's something called platelet-derived microparticles. They're probably more numerous than exosomes, okay? And we're now getting to see that these are very important in regeneration of tissue and things like that. And like an exosome, what do they have? Messenger RNA, all sorts of different RNAs, and basically they're called extracellular vesicles, okay? And they're very similar to exosomes. So remember now, platelets have that, okay? So here we are, I'm comparing exosomes from stem cells and the same sort of thing, the microparticles from platelets. And you can see here an activated platelet and a stem cell, they very much do the same sort of thing. They basically help communicate things. Now we can get these by high-speed centrifugation. For those of you that are involved in our network, we're going to give you a method of how to do it. But I'll show you one of the other things that the platelet microparticles do. Basically, they're involved with macrophages, killer cells, monocytes, neutrophils, and endothelial cells. They promote something called a macrophage too. And we're going to get into macrophages. There's a couple of different types of macrophages. And that's a very important thing, especially in today's age with the COVID-19 virus. Okay, again, activated platelets. What do? They give you these microparticles, and you can see they have many different effects. Now, how do we get these things? We use high-speed centrifugation. And we have a method now that we're able to get these things. And this is basically very similar to exosomes. We still don't know all what they do, though. Same thing with exosomes. We're not sure, how safe they are in the long run, what they do, et cetera. But we think that the platelets, at least, are pretty safe. The exosomes from the stem cells, I'm still not sure about, okay? So what do we have in a PRP product? We have platelets, we have neutrophils, we have monocytes. Now, a lot of people try and put monocytes and macrophages together. Now, macrophages, remember, are found mainly in the tissue. Monocytes are found mainly in the circulating blood. Monocytes are very important. I'm going to get into that in a little while and tell you why they're so important. Okay? We have endothelial cells. Now, believe it or not, in the PRP product, you have some HSCs, hematopoietic stem cells. And then you have one of my favorites. It's called a pluripotent small embryonic-like stem cell, or called a B cell, very small embryonic-like cell. Okay, now, back in 2017, myself and some of my good friends down in Brazil published a paper. And in the paper, we tried to give a classification. We call it the Marspil, and basically it's a classification based on the harvest method of the PRP, how you activate it, if you have red cells present, the number of spins, image guidance, leukocyte number, and light activation, photomodulation. Okay, so here's where we now need to talk about the science. That's what I call the scary urban legends of PRP. There's a big misconception out there that red cells and white cells are very detrimental. Especially if you're treating a joint. They say, well, leukocyte-rich should never be used in a joint. Yes, it may help in a tendon, but not in a joint. Well, if you look at the literature, there's not really good literature that supports that, okay? There's an occasional article here and there, but there's really not good literature. And I'm going to show you the literature that really does support the use of a leukocyte-rich. All right, so are white cells and red cells good or bad? Well, there's a perception out there that a pure PRP, which significantly diminishes red cells and white cells, is a better PRP for many different choices, not supported by the literature, okay? Now, a lot of people say, yeah, but when you start having red cells in a PRP product, it causes a lot of inflammation. Really not the case, and I'm going to give you a couple of clinical examples now. Well, let me show you this first, and then we'll get to the clinical examples. So here you are here. I want you guys to read about William Parrish. He has a number of articles. These are really key articles. And he says here, the non-platelet components of whole blood, such as red cells and leukocytes, are also essential. And they basically include growth factor release, okay? So getting back to the RBCs. RBCs are really not inflammatory. I'll give you a good example. You have a patient who gets an ACL tear of his knee. He gets a hemarthrosis. He doesn't really get a lot of inflammation. He may have pain from the hemarthrosis pressure, but it's not because he has red cells there. But a more important thing, I'll give you another example. You have a patient who had a spinal tap or something, or you did an epidural, and they get a spinal leak. How do you treat that? You take whole blood from a vein, and you give them a blood pack. If something were so inflammatory, such as red cells, would you put that on top of the door? No, you would not, okay? That's my point. Red cells really are not inflammatory like a lot of people make it out to be. Now, more importantly, though, if we really look at the science, red cells can actually stimulate phagocytosis, and it can actually release anti-inflammatory growth factors. IL-10, which is a fabulous anti-inflammatory growth factor. I call it cortisone with no baggage. And TGF-beta-1, okay? Very important in regeneration of tissue. Now, how about white cells? Okay. White cells, again, have taken a very bad knock on things, okay? Now, the next slide is really an important thing. This comes from the work of Parrish, okay? Now, what we're dealing with here, most of the time in regenerative medicine, is what we call an aseptic injection, okay? Now, when you have bacteria, or you have, let's say, a COVID infection, God forbid, or something like that, what happens there is not only are your neutrophils primed, but they become activated. And when they become activated, their job is to go and destroy that microbe. be it a bacteria or virus or something, and it does that by a variety of what we know inflammatory growth factors, okay? However, if the neutrophil, the white blood cell, is primed but not activated, as it would be in an aseptic injection, what do you get produced? TGF-beta, interleukin-10, IRAP, interleukin-1 antagonist. So it acts as anti-inflammatory and is conducive towards building tissue. This is why you don't want to get rid of these neutrophils, because yes, indeed, by using a PRP product with leukocyte rich, you're going to get more of a flare. The patient's going to have more pain for a few days, but in the long run, you're going to have much more success. Okay, and this is just some literature I gave you that shows you that from Brian Cole and Lisa Fournier. They said, look, there really wasn't much difference in the safety profiles between leukocyte rich and leukocyte poor. So it's not like leukocyte poor can cause you much less problems. It won't. Okay. So basically, the bottom line is you'll get a reduced flare when you use leukocyte poor, but it's because you're not getting the efficiency of the PRP preparation. Keep that in mind. It's a very important concept. And again, I've given you the literature there, William Parrish, a number of different articles with good science about that. Now, here's some other important facts about a simple PRP. Now, we're not getting into the esoteric here. We're talking about simple PRPs. Look at whole blood, leukocyte poor, leukocyte rich, and just platelet poor plasma. Across the board, we see a much higher increase of growth factor release from leukocyte rich, okay? This is why you need to use it, okay? You need these growth factors, okay? You know, you're struggling as it is sometimes with the age of the patient. The more growth factors you can release, the better. All right, again, this is another article I have from 2019. And again, it shows the same thing. It shows basically leukocyte rich, leukocyte poor, bone marrow aspirate, bone marrow concentrate, etc. Same sort of thing. So you can see there's a lot of literature out there that really does support leukocyte rich over leukocyte poor. Now, what else can I give you guys idea-wise to make a better and more efficient PRP product? Well, one thing we know is that a temperature of 4 degrees centigrade seems to increase growth factor release. Now, 4 degrees centigrade is a magic temperature in the world of biologics. It seems to affect many different cells and does some interesting things. And I'm going to get into that later on in the talk. Now, another important fact about making a more efficient PRP is if you dilute your plasma with saline to 25% concentration, that also seems to release more growth factors. And this is from an article in 2018. Good article, suggest you read it, okay? Now, matrix metalloproteases, okay? Basically, there's some good and there's some bad, but this is kind of talking about A2M, okay? And basically, are they good or bad? Yeah, there's good and bad, but let's get to the A2M itself. Now, I know Jim has a lot of experience with it, and he's had very good results with neuropathy especially. I'm not exactly sure why we're getting such good results with the neuropathy, but I can tell you it does work. I've seen it for many doctors I have in my network, and it works well. Now remember, A2M is not made in the marrow or something. It's made in the liver, and it's also made locally by macrophages. So again, you want to keep your white cells, okay? Very good treatment for neuropathy. You can always ask Jim. I consider Jim one of the experts on A2M for neuropathy. If I have a question about it, that's the guy I'm going to talk to. Okay, now, I'm drinking my iced tea, by the way. Another process that we know about is orthokine, regenokine, or senokine. This is a process that was started basically in Germany. And what we do here is we'll take whole blood, put it at 38 degrees centigrade, which is basically body temperature, for about 3-4 hours. And then basically we'll take out the supinate, we spin it down. And what we produce is IRAP, okay? Interleukin-1 antagonist, okay? Very successful, especially for that patient that did not seem to do as well as you wanted to. Sometimes when the patient didn't do well, you go ahead and you give them this, you make this product, and that's it. Now, what you do when you're making IRAP, or basically the orthokine, is you basically put your whole blood with glass beads, and that's what you incubate it. You incubate it with glass beads. Dr. Peter Willing in Germany is pretty much the master of this technique, and he's had good results. He feels you're making a lot of interleukin-1 antagonists. He feels you're also producing more in the way of exosomes, so it could be. Now, I want to get to another concept. A lot of people throw these two terms around thinking they're synonymous, angiogenesis and vasculogenesis. You know, I write a lot of questions for doctors on stem cells and things, test questions, and I always put this as one of my test questions. Now, when you have vasculogenesis, oh, sorry about that, let me go back. Vasculogenesis, basically, you're building blood vessels where there weren't any. You're making new blood vessels, okay? Whereas angiogenesis, you're using existing blood vessels. Now, they both work on the concept of hypoxia, but here's a big point I want to make, and this is a very important clinical point, okay? If you have an area that has some existing vessels, such as a muscle injury or something like that, tendon injury, which is near muscles, you can probably do well with just a PRP. Why? Because PRP is fairly rich in vascular endothelial growth factor. But if you have a joint or something like that where you don't have too much in the way of blood vessels and you need to kind of get some blood supply established, you need SDF1, and that's going to come mainly from stem cells. So that's why I typically tell people, and I tell my patients, I say, look, for a tendon problem, muscle problem, we can get by with a PRP. But when you start doing a joint or some avascular structure, you need to use stem cells right from the get-go. And this was back in 2005, and it still exists today. Now, let's talk about stem cells. Anybody out there know the most important stem cell? Jim, any idea? I don't want to put anybody on the spot. So I want you guys to think about it. Most important stem cell. All right, so here we can see the various types of stem cells, the stem cell hierarchy. We have totipotent cells, and we go down to the progenitor cells. Let's kind of take a better look at this. So stem cell, kind of the definition, it's self-renewing, it's long-lived, low proliferative capacity, whereas a progenitor cell is the opposite, short-lived, non-self-renewing, high proliferative capacity. Okay, so this is a concept I want everybody to get because this is a very important concept in regenerative medicine now. The difference between cell senescence and cell quiescence, okay? A quiescent cell is one that's kind of asleep, so to speak, but it can, under the right circumstances, it can get coaxed into reproducing itself, undergoing cellular division when the right stimuli are applied. Whereas a senescent cell is one that can no longer be capable of cell division. But more importantly, senescent cells aren't just kind of hanging out there. They're causing damage. They're much like a zombie in that they'll secrete a variety of inflammatory cytokines. They will basically take over other cells. They'll secrete inflammatory cytokines and basically are a precursor to diabetes, cancer, etc. And senescent cells can certainly diminish your success in regenerative medicine. Now, there are ways of taking care of these cells. We'll get into that shortly. Now, what causes senescent cells? Well, you have epigenetic factors. Oh, sorry again. You have telomere erosion, very important one. Okay, you know, the telomeres, end of the DNA. DNA damage, and one of the most important things, and a really very important subject in all of regenerative medicine, mitochondrial dysfunction. When your mitochondria are not working, your cells are not going to do well. Now, what else happens? Well, we don't get much nutrient sensing, the function there, but what are the real effects of senescent cells? Well, you have basically stem cell exhaustion. That's a big problem. Once your stem cells are no longer fit, you're not going to survive. Basically, just a little fact for you, you'll live 2 days if your stem cells stop functioning. The other important thing about cell senescence is chronic inflammation, right there. Okay, so basically senescent cells are pro-inflammatory, okay? They are a huge problem, and a lot of universities and companies are now pursuing these cells in great detail to try and get rid of them. We're treating patients on a daily basis in our office with things that can kill the senescent cells. Okay, so basically this is another slide that shows the same thing, but let's get into more things. Now, here's a good study. Some of you are doing orthopedic type conditions. Well, Johns Hopkins University has an experimental drug called UXB0101. And what they're doing is they're giving this to people orally. Occasionally they're using it as an injection. And what they're doing is they're having excellent results in treating osteoarthritis. They're not using stem cells now, okay? They're just basically getting rid of these senescent cells. Now, what are some of the things that you can do in your office as far as supplements that you can use? Well, you can use something called fistin. That's basically a supplement, comes from strawberries and red berries and things like that. Vitamin E3, the tocopherol 3 form of it is another one. And curcumin, quercetin. These are things that we know are good for us, but we didn't know why they were good. And now this is why, because they help eliminate a lot of these cells. Okay? So we now have a new science called Senotherapeutics. So Senotherapeutics is basically three prongs. We have senolytic agents, which kill the senescent cells. We have xenomorphic agents, basically they modulate the function of the cells. But you must remember, ultimately your immune system has to get rid of these cells. It has to clear them. So if your immune system is not working too well, you're going to have trouble clearing these senescent cells. Okay, so again, Senotherapeutics, this is a slide you can go back and look at your leisure, kind of read about it, maybe go read about it a little more, but it shows you the various mechanisms of action of these different Senotherapeutic agents. Okay, now what induces or inhibits senescence? Quercetin, okay? And the company I use to get my quercetin is the same as I use, or I should say the same as a lot of universities use. It's a company called Thorne Research. It's located in the United States. Many of these things are over the counter. But the other senolytic agent that we're using is something called destinabit, okay? Now that is a leukemia medicine. In the United States, that medicine is about $500 per pill. I found a source in India, it's about $5 a pill. And we're using this, we're giving it on a basis of one day, and then we're repeating the dosage again a week later. And we have very good results in a variety of different conditions. Okay, now here's again some information. This is coming from the Lancet. I don't know, some of you may be familiar with idiopathic pulmonary fibrosis, really no good treatment for it. And they had significant improvement in the patients just by giving them these senolytic agents. Okay, so that's a good thing, okay? And then we're talking about the destinabit. You know, it depends on the patient's age, but, you know, I would say you could even go to probably to 50 years old. An obese individual, maybe even younger than that. And I give you some dosages here of the quercetin, okay? And you go by the pounds of the patient and the destinabit. And this is giving us very good results. I can attest to this clinically, how good it's working for a lot of my patients. What other senolytic agents are? Well, interesting enough, metformin, diabetes medicine, also good for anti-cancer, also good for anti-aging, quercetin. You have destinabit, you have quercetin again, and foxo, which we'll talk a little bit later about. Now, the problem with the senolytic cells is there's not one agent that can really get rid of all of them. So that's where we're still kind of stymied, because certain senolytic cells in the body respond to one, and then maybe senolytic cells in the liver another, and senolytic cells in the heart another. So we still have work to go. Okay, so I want to move on now. A lot of times you may be looking at some articles and you see something that says CD, CD43, CD34. What this stands for is cluster of differentiation. This is a marker on the cell surface, okay? It lets us know what the cell is. It gives us an example, and I can give you some examples here. Mesenchymal cells, CD90, CD70, hematopoietic cells. So just keep that in mind. That's what it really means. It's a surface marker. It just kind of gives us a little bit of an identity of the cell. Now, when we're looking at a stem cell procedure, we want to know how effective we are. You know, you can look at it under the microscope, you can do a cell count, but really the only way to tell if you're really doing something worthwhile is if you're getting a lot of stem cells is to do what they call colony forming units, where you literally send a culture of the cells, put it in media. It takes a number of days, but that tells you really how efficient you are in harvesting bone marrow, or if you're repairing fat, how that's going. All right, so basically it's what we call colony forming units. It's really fibroblast colony forming units. And basically, it's pretty much the gold standard of figuring out how you're doing as far as stem cell analysis is concerned. Now, what major types of autologous cells exist? Well, there's embryonic, there's mesenchymal, hematopoietic, iPS, very small embryonic-like stem cells, and immune cells. By the way, I asked you guys the most important stem cell. The answer is, well, I'll give you another example. What's the most important instrument in the symphony orchestra? They're all important. Same thing with stem cells. There's not one that's more important than another. They all work as a symphony. There's not like one that's just going to do all the magic. Okay, embryonic cells. Now, embryonic cells are pluripotent, high level of plasticity. They're probably very good for disease modeling, but there's a lot of disadvantages of using these in people. One big disadvantage is graft versus host disease. That can be life-threatening, okay? They also are very aggressive. They can cause disease transmission, ethical considerations. So basically, there's a lot of problems. They can also form teratomas. So really, in most circles nowadays, embryonic stem cells are not really the magic cells we thought they would be. And there's really not much use for them. Now, one thing I have to say about embryonic cells, and this is an important fact for you guys to know about, something called the Yamanaka factors. I call these the footprints of embryonic stem cells. But what happens, these factors, which are basically transcription factors, which a transcription factor basically affects the genes. It can turn genes on, it can turn genes off. When you see these certain factors like OCT4, SOC2, what that really means is that that's a cell that has probably pluripotent tendencies. So that's something to keep in mind. That's when you see these, that tells you that that cell is somewhat interesting and somewhat important. Okay. So moving on, we go to the iPS cell. An iPS cell, I'll get one of your skin cells and I'll treat it I'll reprogram it with either a virus of some type or possibly an enzyme. Now, there's been some problems with these cells. There was a study being done on blindness a couple of years ago. It had to be abandoned because when they treated it with a virus, it seemed to stimulate something called an oncogene. Oncogene is basically a cancer-producing gene. So some of the cell lines were going towards cancer lines. Doesn't seem to be as much of a problem when we treat these with enzymes, okay? But you can see here now, what do they have? They have the SOC2, OCT4, so that means that these are pluripotent type cells. And it's your own cell, which is nice, so it basically is not going to attack your body. Right now, we use them for human disease modeling, drug screening, and probably eventually patient-specific therapy. So an important cell to know, okay? Somatic nuclear transfer cells, okay? So what I do here is I would get one of your cells, I would take out the nucleus, and I would transfer that nucleus into an unfertilized egg. Now, what happens, this is basically cloning. It's a very slippery slope. And then what we have to do is once we put that nucleus in there, we have to treat it with electrical shock. But what happens is we start getting reproduction. And luckily, we're not able to reproduce a person right now. But here's the interesting thing about this technique, okay? Now, we look at some work done at the University of Oregon. And what they found is that when I take the nucleus from an adult and I put it in this unfertilized egg, the telomeres become longer. We're basically reversing aging, okay? So there's some very important aspects there. And we may use this technique eventually to probably make some body parts. I think that's where we might end up doing some things. Now, here's one of my favorite topics. This is called very small embryonic-like stem cells. There's a number of different names for these cells: stem biocells, blastomeres, B cells, etc. These are pluripotent cells. Now, these are found in each and every one of us, okay? And they basically, interestingly enough, these cells produce telomerase. Now, the interesting thing about these cells is they're very small, and this kind of gives you some ideas here, but they can differentiate into any type of tissue. Now, basically, for us to do these kind of cells, it's a 3-day process. On day 1, we'll give the patient either some vitamin A, or we'll give them some CoQ10, or sometimes we give them an algae called Phagocytosis. Phagocytosis is an algae found off the coast of Okinawa, and the people of Okinawa, as you know, are longest lived in the world, essentially. And it seems to stimulate the production of these cells in the bone marrow, and it releases to the circulation. But the problem is, when these cells are released to circulation, they are quiescent. Remember, a quiescent cell is one that can reproduce under the right circumstances, okay? So what do we have to do with these cells? Well, then we harvest them the next day. Then we have to put them at 4 degrees centigrade overnight, okay? Remember, 4 degrees centigrade is a magic number. We also put them in a hypoxic chamber, so they're not really getting any oxygen. But by doing that, these cells become activated. Now, an important thing is these cells are found in non-centrifuge bone marrow. Probably also occasionally found in PRP. Okay, so you can see here, this gives you an idea about the cells, and they're very small in size. Okay, now interestingly enough, these cells seem to be related to acupuncture. So what I've always said is acupuncture was probably the first stem cell procedure known to man. Because there's something called a Bonghand channel, and I'm not an acupuncturist, and I'm sure some of you know a lot more than I do about acupuncture, but these are channels found throughout the body, and we found that these channels, and this is from a fellow in North Korea, a doctor in North Korea, but we found that these channels are very rich in these V cells. And that's probably why someone who really knows acupuncture is getting such good results, because he's stimulating the V cells and activating them, okay? Now, when you have a V cell or when you have a pluripotent cell, the DNA is very wide, okay? When you have a cell that's very differentiated, you can see it right here. The DNA is very compact together, okay? Whereas it's called a chromatin. Whereas when you have a pluripotent cell, the DNA has a lot of space in it. It means it can do a lot more. So just keep that in mind. Now, interesting thing about these cells, here's one of the real keys. When we give these cells back intravenously, a number of the studies have shown that these cells seem to increase the telomere length of the cells of the immune system. Now that's one of the holy grails in anti-aging medicine. If we can make the patient's immune system younger, we're going to make him younger. We're going to basically allow him to fight off all sorts of diseases such as cancer and things because his immune system is going to be more efficient. And you can see here from this article, it basically increased the telomere length. Important fact, okay? Now, one of the things we found about these cells is that they're very sensitive to parathyroid hormone, very small amounts, okay? Has a very big benefit. So I kind of checked on that further and I said, wow, there's a lot of interesting things about parathyroid hormone. Here's an article from NIH. Parathyroid hormone, that's triparatide, is basically chondroregenerative. So basically, if I give small amounts of, parathyroid hormone, I'm going to help regenerate the articular cartilage. But here's even another important fact, okay? Intermittent amounts of parathyroid hormone basically stimulate the bone marrow to produce more stem cells to the circulation. So now I have a compound that's causing chondroregeneration, increasing stem cell output. It's an ideal thing. And we have a fairly inexpensive way of doing this by some oral growth factors that we give. We can also use it with an iontophoresis patch. So if you get parathyroid hormone itself, it's extremely expensive. The way we do it, it's, $20, $30 US, maybe a little more. Okay, so let's talk about mesenchymal stem cells. Okay, if you talk to Dr. Arnie Kaplan, he'll say, wait a minute, I was mistaken. I'm not sure these are even stem cells. Okay, so he's not, convinced that they're stem cells. Anyway, what does an MSC do, a mesenchymal stem cell? Basically, it does immune modulation. It gets the inflammatory process down, okay? But there's some exceptions, and I'm going to get into those in a little while. So Dr. Kaplan now says, hey, we should call these medicinal signaling cells. All right, now basically what they do is they start out on vessels. They're called periocytes. And given the right circumstances, they become activated, and we can see from this slide from Dr. Kaplan's work, they become activated MSCs, regenerative MSCs. They can either do immune modulation, which is extremely important for them. They can even do some, regeneration of the tissue itself. Now, basically what I kind of do, in the United States, we have a very specialized part of our armed forces. They're called the Navy SEALs. And they're very specialized. They go into an area that's very hostile. They may not survive, but you know what? They hopefully secure that area so the rest of the cells can do their work. And the MSCs are the same thing. They go in a very hostile area. They may not survive, but they make it so other cells can go and do their work, okay? Now, here's the question that everybody should think about. We can give MSCs intravenously sometimes, things like that, when you use SVF, let's say, or you can put them in a knee joint, and they only last a few days, yet some of their effects can last for years. Why is that? Well, this is one of the most important slides of the whole lecture right here, okay? This is a landmark article because what it says here, immune modulation by therapeutic mesenchymal cells is triggered through phagocytosis of MSCs by monocytes. And I got this article from Dr. Arnie Kaplan. He and I were lecturing last year in Hawaii, of all places, and it was interesting. There was probably about 15 people attending this whole lecture, including the speakers. So it was like wonderful. We just kind of interacted with each other. But this is a landmark article. And here's my little picture, so to speak. So you have a monocyte that goes after an MSC, and what does it do though? So it forms something called a Treg cell. Now we're getting into some of the immunology that we need to know. If we're going to do regenerative medicine, you need to know immunology. If you don't want to know immunology, please go and do some other type of specialty because you have to know this stuff. So what is a Treg cell? Well, if you don't have too many Treg cells, you're going to have an autoimmune disease that's going to bother you. So what happens is the phagocytosis of the MSCs basically produces Treg cells. And Treg cells last for years. They produce anti-inflammatory cytokines. They help reproduce tissue, etc. So this is how the MSCs are really working. So that's the real key here, okay? And this is just a slide that kind of shows what I'm saying. Okay, so the importance of Treg cells, I can't stress to you how important they are. Now, let's take this one step further. You know, when we're talking about the COVID-19, we're talking about some people who get what they call a cytokine storm. Well, what happens there is basically the body in its zest and zeal to eliminate the virus is going overboard. It's not stopping when it should stop. So not only is it destroying viruses, it's destroying other tissues. It's basically attacking itself. Tregs will calm that down. It'll do immune modulation. And that's why we're thinking maybe mesenchymal cells may help, at least in the COVID-19 cytokine storm. That's the whole idea about that. And again, we see MSCs in relation to Treg cells. Okay, now, there's some people that talk about using allogenic MSCs. And they say, oh, you can use these cells because they're great, they're immune privileged. Well, they're not immune privileged. They're what I call immune evasive. If you're using MSCs from another patient, eventually the body's immune system is going to get them. May not get them right away, but it's going to get them. And there's also a risk that you could potentially get a graft versus host disease or some other big problems. So I'm not sure what the legal law is in the Philippines as far as using these cells. In the United States, umbilical cord stem cells, et cetera, they're probably also those products don't have them anyway, but they're not allowed to be used. So, and bottom line. Now, here's some of the things we see from MSCs. All sorts of different factors. But here's a very interesting factor: antibacterial, antiviral. Okay, so yes, again, an MSC itself can go after the COVID-19, but more importantly, mankind has to thank MSCs for our existence. Okay, I'm going to give you a good clinic example now. You have a woman during her menstrual period. Basically, it's an area where there's much bacteria, there's blood, etc. It is a setup for a sepsis. Yet most women never get any sepsis. Why? Because menstrual blood is very rich in MSCs, which basically kill any potential bacteria that could take a foothold. So very important. Okay, now stem cells and the immune system, the unbreakable bond. Okay, we really learned a lot about this with all the new COVID things like that. But there's two types of immune systems we deal with basically. There's the innate, okay, which is the antimicrobial, and then there's the adaptive, so we're saying, okay, hopefully if you get this infection, you're going to develop antibodies and you'll be immune to getting it, or you could maybe donate some of your plasma to a patient who has it. So that's the difference between the two. And you can see here how they work in the innate immunity and the adaptive immunity. Okay, so we have a couple of different forms of stem cell immune systems, et cetera. We have the T1 system, which is cell-mediated immunity. Okay, it doesn't involve antibodies. It basically is going after these things with T cells and things like that. Then we have the T2, which is the humoral antibody. So basically, if you're going to get an infection with the COVID, you're going to hope that your Th1 is going to really do the trick and get rid of this virus for you. Whereas if you basically had an infection and you want to get protected, it's going to be the Th2 that's going to protect you. Now you have the T17, very important in various autoimmune diseases. And then you have our buddy, Tregs. Tregs are what really saves the day for a lot of us. Okay, so again, this is the immune system in a nutshell. T2 is kind of not a bad thing. It can help us with getting rid of some autoimmune diseases. T1, big problem for autoimmune diseases, autoimmunity, rejection, etc. T17, same thing, autoimmunity. And Tregs, graft tolerance. You're gonna have graft tolerance, you're also gonna get rid of any autoimmune disease, things like that. So again, very important things about the immune system. Now we get into some of the very interesting things that you may not have heard before. When most people talk about MSCs, they talk about, oh, it's just an MSC. Well, guess what? There's two very distinct types of MSCs. You have an MSC1, which is pro-inflammatory, and you have an MSC2, which is immune modulatory. So no longer can you just say, oh, MSCs are immune modulatory. It depends on the environment they're in, okay? Now, for instance, a lot of times, again, you're getting a COVID infection, you're gonna get a lot of MSC1s because basically what they're gonna be doing is they're gonna be fighting that virus, okay? You don't want immune modulatory right off the bat. You want it down the road, okay? And you can see here various types of things that help that, okay? Now we go to the next slide here. And MSCs, we start out as an MSC, then depending on its environment, there's something called the toll-like receptors, okay? These are receptors on the MSC cell surface. And given certain compounds, it can make it either be an MSC1, which is gonna be pro-inflammatory, but it's gonna be great for bacteria, great for viruses, or it's gonna be immune suppressive, great for when we're done with the virus and we wanna kind of halt the body's attacking of the virus and the various other cells. Okay, and again, MSC1, MSC2. MSC2 prevents autoimmune diseases. MSC1 can cause it, okay? And now you see that what you thought was maybe very esoteric is really important. If you're dealing with a patient with an autoimmune disease, you want to get over here. You want to get MSC2s. You want to learn how you can manipulate that system to get more MSC2s, okay? And here we are here now. We start seeing how the MSCs work with macrophages. And guess what? To make things even more complicated, we now have macrophage 1s and we now have macrophage 2s. And we'll get into that in a moment, okay? But here's a slide from Dr. Kaplan again, and he shows you the various things of the MSCs. Okay, it can either be immune modulatory and trophic, or it can be antimicrobial, okay, basically bacteria and viruses. And again, another slide that tells you the importance of the Tregs. You can look at this at your leisure, okay? Now we start talking about the macrophages. I call them the center of the immune solar system. They're so important in regenerative medicine. And one of the most important things is this little growth factor right here, IL-4. Because IL-4 can make a macrophage become either a macrophage 1, which is, you know, antibacterial, or it can become a macrophage 2, which is basically cell reparative, okay? So M1s are pro-inflammatory. They possess remarkable antimicrobial abilities. M2s are immune modulatory, okay? And they release IL-10 and trophic factors. So think about it now. When I started talking, you probably never would have thought I was going to tell you that macrophages are immune modulatory. You say, wait, macrophage, how can it be immune modulatory? But it is. Now, here's some slides. This is also important too, because typically when something is regenerating, like an M2, it uses oxidative phosphorylation. When something is not, you know, reproducing things or differentiating, it just undergoes glycolysis. I'll get into that a little later. But here it is here. IL-4 induces macrophage 2s, okay? And basically, the next slide really shows the importance here. Let me go one more slide after that. So here we are here. We start with a macrophage. Given the right neighborhood, you basically get arginase, you get ornithine, and you get basically cell proliferation and repair. A macrophage, believe it or not, contributes to cell proliferation and repair. Whereas here you get inhibition of cell proliferation. You basically, that macrophage is really going and destroying bacteria, and it does collateral damage of destroying tissue around it also. But sometimes you have no choice. Sorry about that. All right, let's see if I can get back to my slide here. Okay, let's see where we are here now. Hold on here. All right, let's see. Here we are. Okay, everybody see the slide again? I hope you can. Okay, so let's see where we are. All right, so let's go to the next slide here. Now, you know, another important cell is hematopoietic stem cell. okay? And HSCs actually are some of the drivers of tissue regeneration. And I give you some of the literature here right now. It says the primary engine of new bone and cartilage formation in vivo, remember now, in vivo, not in vitro, is basically HSCs. And there's some good literature. And this goes from 2001, 2012. So this is not a brand new concept. This has been around for quite some time. It's not just MSCs. It's a whole symphony of things. Now, adipose tissue, treasure trove of stem cells. Okay, now, SVF, basically you make it either with lecithin, you make it with collagenase, you can do ultrasonic cavitation, a number of different ways to get there. But there's some problems when you use SVF. You destroy the structural niche of the fat cells, okay? So that's why I sometimes, want to use a free fat graft in addition to the SVF. I think that makes it work better. And this is what it looks like here. This is actually my SVF way down here. Okay, now here's some very important concepts if you're going to be using fat. There's a big difference between obese adipose tissue and lean adipose tissue. Forget about the size. For instance, you have an obese person, you have a lean person. 5 cc's of cells from an obese person is maybe equivalent to 2 cc's from a lean person. So the cells are much smaller as a lean thing. But more importantly, again, now we go back to the immune system, we go back to the basic science. Look at the cell profile in obese tissue. Treg cells, 1 over here. Lean fat, we have 3. Okay, M2s, 1, 3. Okay, so now you start seeing why is it that you'd want to try and use lean tissue rather than obese tissue. Now, we have ways of treating that. We can treat patients. If I have a patient, sometimes a couple of days ahead of time, I'll give them a patch that has some IGF-1 and some IL-10, and I can make that obese tissue become more like lean tissue. Or I can basically put a patch on the knee with IGF-1 and IL-10, and it'll actually help bring me more towards this area here, which is much better for cell regeneration. Again, another picture that shows the same thing, a lot more M2s and only 1 M1, and the opposite in the obese. That's why obese people have all sorts of, metabolic X syndrome, all sorts of things associated with obesity because of these bad cells in there. And you can see it right here. Okay, and then again, we see it from here. So these are good slides for you to look at. And if any of you are doing SDF, you really want to look at these slides because this really can make the difference between good clinical results and so-so results. Okay, so again, some interesting things that we can see here with the macrophages and things like that. Okay, now mu cell is another interesting cell that's found in fat, found in bone marrow and things like that. Basically, we're working on a way now of obtaining those, and we'll probably have that within the next couple of months. And the mu cells are very interesting because they love stress. The more stress you give these cells, the better. So I'm thinking these cells may be the ideal cell to help regenerate a degenerative disc in the spine, because you probably have no other place in the body that's as stressful as a disc in the spine, okay? And these are pluripotent cells, very high survival rate, and they're found in free fat grafts, also found in uncentrifuged bone marrow. So keep that in mind, okay? Now, when we talk about bone marrow, we only use local anesthesia when we do ours, okay? Bone marrow, anything we do in regenerative medicine is probably the most technique-driven aspect of regenerative medicine. It really depends on your technique to how good you're going to do. The key is, first of all, don't use one of these gigantic syringes. If you go by the work of Dr. Muschler and Dr. Hernigal from France, basically they'll tell you don't use a syringe any larger than 10 cc's. And when you use that 10 cc syringe, take about 3 or 4 cc's tops of bone marrow and then put it down and go get another syringe, because that gives you the proper pull of the cells. And you want to do it rapidly. You don't want to do it slowly. It may hurt more rapidly, but you're going to be able to get a lot more in the way of cells if you do it that way, okay? Again, Dr. Hernigal was giving a lecture in, where was it? In Brazil last year, and he was there and we were talking a good bit about this, and he felt it was very important. And he also said, red cells are not a problem whatsoever. I don't know why people think they're a problem. Dr. Hernigal has been using red cells in his marrows for 25, 30 years. Okay, so basically you want to go basically the posterior iliac crest. You do not want to get bone marrow from a long bone. It's tempting to get it from a long bone. You think it's easier, but it's not. And you're basically not getting very much in the way of stem cells. And don't use a drill. Basically, the drill kills the bone. It's going to give you a hole. It's going to last forever. Just go in, you just tap it in nice and gently, and you'll be able to get your blood. Okay. Now, here's the problem with bone marrow. If you look at bone marrow, basically 1 out of every 10,000 cells in a newborn is an MSC. And as we go on, it becomes 1 out of every 2 million at 80 years old. So using bone marrow alone in an 80-year-old, maybe not the best of things, okay? But, you know, whereas fat's different. But look at this, bone marrow still trumps everything else as far as the total number of stem cells. So keep that in mind, okay? Now, interestingly enough, you know, people say, well, you know, your bone marrow, you know, as you age, the MSCs decrease. Well, that's true. Actually, HSCs, hematopoietic stem cells, increase in number as we age, but their overall effectiveness is about the same because they may increase in number, but they kind of lose some of their efficiency. So there's basically, it's kind of a draw there. Now, other things that can help when you're doing stem cells, hypoxia, okay? So I was one day listening and thinking to myself, how can I get hypoxia? I'd make it a CO2 generator. I said, wait a minute, this is stupid. All I need to do is get a vacutainer. So I put a lot of my things in a vacutainer tube for 20 minutes, and it works very well. And we'll put our fat graft in there. We'll put our bone marrow aspirate. We'll put our PLATELET in there. And that works and works well, okay? So bone marrow versus fat, you got to use both of them to really have good results, okay? Now, the question is, what happens when you centrifuge bone marrow? What are you throwing away? Well, we know centrifugation can damage cells. You know, most people think, oh, centrifugation is the way to go. I don't want to do anything else. There are some people that just take bone marrow fresh out of the marrow and that's it. But I'm not so sure that's good either, okay? So when you centrifuge, you're throwing away mu cells, B cells, probably exosomes, and some cells of the immune system, okay? And here's an article, basically, that really kind of drives home the point. It's from these doctors in India that said, hey, you know, you're throwing away B cells when you're centrifuging bone marrow, okay? So basically, I said, that's a good point. So what we did is we came up with a hybrid system, okay? So, and again, this just tells you what centrifugation does. So what we do is we basically take some of our bone marrow right straight from the bone marrow. We don't centrifuge it, we just put it aside. And then we'll take about 20 or 30 cc's and we'll centrifuge it and get a concentrated thing. We actually published a paper on this and we just got it released back in April of this year. Bone marrow products. We basically did a classification and we had the hybrid. And we can tell you by far, we're going to be publishing a paper on that. Hybrid bone marrow works the best by far. No question about it. Now, when you talk about bone marrow and PRP, let's go back to that. Look at the, you know, you can look at IRAP in particular. Look at the difference in concentration of IRAP, okay? Remember, interleukin-1 antagonist, this really knocks inflammation way down, okay? Bone marrow has 13,432 picograms per microliter. Bone marrow, PRP 588. Tremendous difference. That's why you're gonna have better results with bone marrow, typically, okay? Now, this is an interesting thing. When you start culturing cells, you don't seem to have the immunosuppressive properties like you would think you'd have. It's certainly going to be better because it's just a numbers game, but the MSCs are reduced somewhat. So we have to work on that somewhat to figure out how we can get these MSCs to get better immunosuppressive properties. I mean, right now we're getting it better because of just the sheer increase in numbers, okay? Now, interestingly enough, why do certain joints are more successful than others? And I could never figure it out. I said, you know, the hips don't seem to work as well as the knees and ankles, and I didn't know why. And I came across this article. This was written October of 2019. I believe it comes from Duke University. And what they found is that there's a prevalence of a younger protein that was tied to the abundance of microRNA. And what they found, the next slide should show it better. So basically, they found older proteins were in the more proximal joints, and younger proteins were in the more distal joints. So the bottom line is, the more distal the joint is, typically, the better chance of success you have. So that's a pretty important article because it finally explains to me, because I could never really give you a good explanation. I mean, I would see hips, all right, some of them had a lot of damage, some of them didn't, but typically the knees always did better. And I don't know why. Now I know why, because it's this younger versus older protein. Good article to go read because it's pretty much a landmark article as to why there's a difference in the results of things. Okay, now exosomes. Okay. You know, in the United States, the FDA really does not allow us to use these things. There are people using them, but little by little, that's going to stop. So basically, life begins as an or I should say, their life begins as an endosome, and then it becomes eventually an exosome. Okay, I consider an exosome as something like, and you can see here, we start here, we go here. Exosomes like what I call a DHL or FedEx package. It gets to the right place at the right time. Okay. Now, interestingly enough, exosomes or extracellular vesicles and viruses are very similar in nature, okay? You know, they both have RNA, messenger RNA, et cetera, and they both depend upon their environment, and they basically control the cell by direct programming. You get a COVID-19 into the cell, it's gonna basically hijack that cell and tell it what to do, okay? So they both are cell and tissue specific. So think of an exosome almost like a virus, and I think you can put it in better, you know, shape in your head. Now, there's a lot of different RNAs out there, and I want everybody to know a little bit about it. You know, you have microRNA. Basically, it's a non-coding RNA that functions in RNA silencing and post-transcription, basically gene regulation. You know, that's a really important aspect of medicine now, turning genes on, turning genes off, okay? And you have the tRNA. Basically, it carries amino acid to the protein machine, the cell ribose, basically to make proteins. So just a good thing to know about these things. And again, I said basically right now, FDA, it's non-compliant, you can't use them. We need to do more work on exosomes. They very well may be a very important aspect of treatment. They seem to have a lot of promise, but we just don't know enough about them yet. And again, some more things on exosomes here that you can look at, okay? And again, we need to basically improve their efficiency and their yield. And again, there's certainly limitations with these things. Now, what else do we use in stem cell therapy? Hyperbaric oxygen, okay? Why does hyperbaric oxygen really work? Well, it really isn't the oxygen itself. What it is basically the increase of nitric oxide, and this is basically endothelial nitric oxide, which affects the marrow. And this is from the work of Dr. Tom from the University of Pennsylvania. And what he said to us, he says, nitric oxide causes the marrow to produce large numbers of MSCs, HSCs, et cetera, and release it to the circulation. So that's the true mechanism of hyperbaric oxygen. Okay, now there's some other points of hyperbaric oxygen, but by far that's the most important one of all. And basically it all has to do with nitric oxide. Now, you must realize nitric oxide has different effects depending on where and how it's produced. You have neuronal nitric oxide synthase. Basically, it affects the muscles and nerves, and it can be very beneficial. It can help repair those tissues. You have inducible nitric oxide synthase, which basically is very good for inflammation, killing, you know, viruses, killing bacteria, but also kills cells. And then you have endothelial, which is what we like because that's the one that increases cell output from the marrow. Now, ozone, okay? Ozone is becoming more and more important in biologics. Now, when you treat blood, and we have a way of treating the entire circulatory system, you basically get these compounds called ozonides, okay? Now, ozone therapy is a critical influencer on oxygen utilization. And what it really does is it really has an effect on NAD production, nicotinamide adenine dinucleotide. Also, it produces various cytokines, okay? But here's an important thing. And now this is another thing that everybody should start learning about. Basically, NAD and the importance in regenerative medicine. It's so, so important, I can't tell you. Because it can make or break your success. NAD can help those mitochondria become much more healthy and things like that. This is some of the various things that ozone itself does, okay? I just want you to read these at your leisure. Okay, but another important aspect of ozone therapy, you go back, it basically stimulates something called the NRF2 pathway. And this is a very important pathway in regenerative medicine because it's the master regulator of antioxidant and cell defense genes. Basically, it reduces inflammation. If you can stimulate that pathway, you're going to reduce inflammation. You're going to give the stem cells a much better chance of doing their, doing their work. And this shows you some of the effects of ozone. Many times we'll inject ozone directly into the joint. I have someone that works with me. He's using ozone in his spine with very good results. Sometimes we just put it in the muscles and it seems to help eliminate the pain. So pretty interesting thing, okay? And you can see here the various pathways that it works on. Oxidative stress is dramatically reduced. Getting oxidative stress down, again, is basically a form of immune modulation, okay? So we use ozone, basically 20 micrograms per milliliter. And this is an interesting machine. Here you can see a machine. What we have here is a dialysis filter. We have one line going from the patient to this machine. It ozonates the blood and it puts it through a dialysis filter, and the other line goes back into the patient. Very interesting. Shockwave therapy. Okay, basically it's a mechanical stimulation of the cells, and it produces a number of cytokines. It's very important, and it's good in chronic inflammation. I've been using this thing for probably 15 years or 20 years. Even before I did stem cells, I was using shockwave therapy. These are some of the things it does. It changes the cell membrane permeability. It has antibacterial effects, releases nitric oxide, releases growth factors, induces vessel growth. Here's a great article about shockwave therapy. It's from China. And what they really found is what the shockwave can do is it has a very profound effect on the mitochondria of stem cells. It makes them bigger and more numerous in number. And then here is an article also from Harvard. And what they found is shockwave therapy induced the production of lubricin in joints and other areas. Now, lubricin is basically a very high-powered hyaluronic acid. And that's the best thing you can have on a tendon because you want to get that tendon to glide nice and smoothly. So lubricin production is also made by shockwave therapy. Now, you basically don't want to use any local anesthesia with shockwave therapy because it can alter the biologic effects of the shockwave therapy. Now, lubricin itself is a very important thing for bone-on-bone arthritis. It's a high-powered hyaluronic acid, but talking about hyaluronic acid, it's basically not just a lubricant, it's a singly molecule, has many biological roles. It helps in cell behavior. It's a direct mediator of gene expression. So hyaluronic acid is a very important molecule. It's a key player in tissue regeneration. We have patches that we use that have various growth factors in it, and each of those patches has a high molecular weight hyaluronic acid. Low molecular weight is actually pro-inflammatory, so you don't ever want to use that. Now, you may read a study that says they did the study and they used saline as a placebo. It's not a placebo. Brian Cole had a very good article back in 2016 that said, hey, saline is a therapeutic agent. So keep that in mind. If you ever see anything that's talking about saline as a placebo, throw that article out. Okay. Photoactivated PRP, stem cells, etc. This shows you some of the things that they do. Basically, you have healing and anti-inflammatory aspects. You have growth factor release, interleukin-1 and interleukin-2 antagonists, beta endorphins, exosome production. Really, a lot of interesting things with that. Here's a good article on the effects of phototherapy on neutrophils. I can tell you, we use phototherapy on everything. Now, when we use a PRP, if we use phototherapy, we get almost much less inflammation than we normally get otherwise. And here's a little machine. We're actually in the process of making a machine now that we think will be much more effective than this and much less money. Okay, that's the Addy light. Okay. Now, what are some of the downstream effects of light therapy? Transcription and stimulation of genes. Lights can turn on and turn off genes. Basically, certain therapies, certain wavelengths can have an effect on the mitochondria, especially. So the mitochondria are the principal photoreceptors when you're doing light therapy. Light therapy does work with regenerative medicine, especially the red light wavelengths, because they really affect the mitochondria of cells and they can make them much healthier. And again, this shows you some, and you don't have to just use lasers. I mean, we're using LED lights for stimulating our PRP, bone marrow, aspirate, fat, etc. LED works very well. You don't need the intensity of the laser nor the heat of the laser. Okay? Now, when you're talking about what you should do afterwards, we published a paper on this back in 2018. This is an interesting paper because it really dispels some of the major thinking in PRP. Okay, here's basically some of the key points. Now, look at number 4. The use of non-steroidal anti-inflammatory is generally safe in the acute phase and early subacute phase. You know, everybody reads this article, oh, well, you can't use anti-inflammatory for 6-8 weeks. There is no science to support that, okay? Anti-inflammatories can maybe have a detrimental effect on normal tissue, but disease tissue doesn't seem to affect. And read that article, we have it in there, and basically what we've given you the literature, why you don't have to worry about this. I've not had any qualms about using an anti-inflammatory in 15 years. And basically the other thing about the article is mechanical transduction. Basically, when you stimulate muscle, you stimulate the various growth factors. And that, again, is going to lead to success. So early PT is mandatory. Okay, we're talking a little bit about basically tendinosis and tendinitis, the various types of collagen that we found is collagen type 1. It's the basis of all things collagen, basically articular cartilage, etc. So tendinitis is an inflammation of tendinosis many times. I'm just giving you some ideas of the two. Tendinosis is what you want to use regenerative medicine for. So we're almost at the end, guys. So we'll talk a little bit about cytokines. We use cytokines basically orally now. We used to use injectables, now we use patches. We don't really use interferesis anymore. And cytokines are basically every condition in medicine is an imbalance of cytokines, either too much, too little, or that's it. So you want to really balance these cytokines, okay? Now, what we've done is we now have patches. This is a patch. This is from my good friend, Dr. Joe Sorrentino. We basically went to a company in Switzerland. We had these produced. They are approved by the FDA. This particular patch may have interleukin 10, interleukin 1 antagonist, has some hyaluronic acid, I believe TGF beta, and basically penetrating molecules. You put it on the joint, leave it on 8 hours. You take it off and throw it away, but you basically dramatically increase the amount of growth factors in that area. And this is what it's called, Senolytics. I put a lot of this on LinkedIn. You can read a lot of these things about it on LinkedIn, or go to my website and read my blogs. But very, very cutting edge of the cutting edge. This is really, I've been using these for years. It's, to me, makes me way ahead of everybody else because I have more growth factors than they can ever hope for. And again, it just shows you how they work. But you can go read about this. This is interesting enough to read about. So interleukin 10, IRAP, things like that. And we can kind of speed through that. Now, what are some of the sources of the human cytokines? Well, this kind of was a surprise to me, but one of the interesting sources of cytokines is various plants, okay? The tobacco plant, for instance, they make something called GCSF, granulocyte colony stimulating factor. You may know that as something called Neupogen that they give to patients after chemotherapy. That's derived from the tobacco plant of all things. So really interesting things to talk about, okay? So myokines and their action. Now, myokines are basically cytokines that are found in muscle. And this gives you an idea of some of them. They have some far-reaching effects, the various types. Again, this is something you can go in at your leisure and just look the slides and read a little bit more about it. The various cytokines that you find in muscle. And it's a whole different world, so to speak, of what you're used to. But look at this, BDNF, brain-derived neurogenic factor, found in muscle, of all things. So that's why if you have a patient who's in good physical shape, typically mentally he's in pretty good shape also. And again, these are the major myokines. Brain-derived neurogenic factor, interleukin 8, interleukin 15, FGF21, and leukemia inhibitory factor. So those are the important ones there. And with that, I think I'm ready for questions. A lot of material there. Any questions?
Dr. Joe, thank you very much for such a very comprehensive lecture. And what I can say is you just compressed the regenerative medicine in parts. For those of you interested to learn more about regenerative medicine, you can keep in touch with Dr. Joe. He's doing a lot of training in Florida and maybe some online training as well. I don't know. But this is one of the best lecture that I've ever heard so far about regenerative medicine. And as expected, Dr. Joe is really 4-6 years ahead of his time, all the time. All these materials will soon be available, I think, in other regenerative conferences, maybe 5 years from now. But the things that you learn from him will really be something that you can use and very useful. Now, I would like to open this, if you can just bring back the screen, Dr. Joe.
Sure.
I want to see your face, and everybody would like to see your face as well. So is it possible to just remove the share screen?
Okay, let's see. Okay, let's end the program first.
Okay.
Okay. All right, now let's end this. Okay.
And then, yeah.
We get
So
PowerPoint.
there's a lot of questions that he would like to ask you. So
Don't be ashamed or embarrassed, okay? I know there's a lot of stuff there, but don't worry about it. All
okay.
right.
Okay, again, congratulations, Dr. Joe. That was such a very comprehensive lecture. Very nice, very in-depth. So let me see. Who would like to ask the first question? Anybody?
I'm not going to bite you.
Dr. Joe? Dr. Joe?
Okay, Dr. Domingo, go ahead. This is Jojo. He's in the planet Mars.
And congratulations for an excellent lecture, sir.
Thank you.
I would just like to ask if, what do you think about fasting to reduce senescent cells?
I can't quite hear you with the mask on. What was the question?
What do you think about fasting to reduce senescent cells?
He's asking fasting. Fasting,
Okay, well,
Dr. Joe.
what does fasting do? Okay, fasting, that's another talk I have. Fasting stimulates a lot of stem cell aging pathways. Fasting will stimulate autophagy, which will go after and get some of these cells and take some of their parts out. It'll stimulate the SIR2 and 1 and 3 and 6 genes, basically an important thing, NAD, etc. Fasting is very important. A good thing for anybody doing regenerative medicine to have their patients fast. Intermittent fasting is very good, very good for anti-aging, etc.
Thank you very much, Dr. Joe.
No problem. Oh, it's you, Jojo. Okay,
Yeah,
I couldn't see.
Yes. Okay, there's a question here. What's the difference between fibroblasts and fibroblast growth factor?
Well, fibroblast is a cell. Fibroblast growth factor is not really just for fibroblasts. It's for many different cells. But I mean, initially when we did the science, it was mainly looking at fibroblasts. When you look at MSCs, they're forming fibroblasts and things like that.
Okay, Dr. Joe, I have 1-2 question here regarding your M1 and M2 macrophage. Is it automatic that during the early phase of the inflammatory process, we would initially, the cells would initially be M1, and towards the end of the inflammatory phase, it would be primarily M2?
Well, that's exactly right. Remember now, these cells basically get turned on by the neighborhood. So when you start having an infection, first of all, you're going to have your MSCs. They're going to start secreting inducible nitric oxide synthase, which is going to make NO that's going to basically turn these into MS1s, macrophage 1s. Now, as you start getting rid of some of these things, you're then going to see a turning to go to macrophage 2s. So it depends on the neighborhood. Initially, you're always going to get macrophage 1s to attack the bacteria or attack the virus. Now, hopefully that turns down. But unfortunately, in some people, it doesn't turn down. It keeps on going and building. And that's when these people get the cytokine storms.
I see. And then the other question is, with regards to your nitric oxide sources, because we have here arginine plus, or just a plain arginine tablet. So would it be a good source for arginine as a supplement after regenerative procedure?
You have to use what you're able to get. Now, in all honesty, I think the best source out there by far is a company called Human, Humann, and they have a product called NEO40, NEO-40. This comes from the University of Texas. Dr. Nathan Bryant, who's probably the world's expert on nitric oxide, was the one who devised this, and it's the best form out there, nitric oxide. But I don't know how available it is in the Philippines, and I don't know what the expense is there. So arginine is a reasonable substitute, but not as good. Beets basically come from beets. So every patient eat beets or drink beet juice and things like that.
Okay.
Doctor, can I
Yeah.
ask?
Okay, this is Pash. Okay, Pash, go ahead.
Good evening, Dr. Joe. Thank you so much for such a comprehensive lecture.
Well, good morning to you. Okay.
Yeah, good morning. Yeah. So I was just wondering, you said something about being able to convert obese adipose tissue into lean adipose tissues, right? I think it has something to do with IGF-1 and IL-10. So have you ever seen like a window to help obese patients to actually address this problem about obesity by, you know, changing it into more lean adipose types of tissue instead of the obese types of, you know, from the problem about those tissues?
Well, you know, I don't know exactly what the mechanism would be, but I would assume if you have an obese person who becomes lean, you know, you're going to get the change in cells. I mean, we know that when someone loses a lot of weight, mysteriously their health improves dramatically. And it's basically because of the cell profile. Now, what we do is basically, you know, most of these people are not going to go lose a bunch of weight. So I'll basically pre-treat them by putting it on the carotid arteries. And that gives me some extra IL-10 and some IGF-1 in the system. But more importantly, a lot of times if I use a free fat graft, I'll just put that onto the joint because it's going to help basically polarize it to more like a lean thing. I mean, it's not going to make it totally like a lean, but it's going to help some. And the patches are fairly inexpensive. They're about $15, $20 a piece. They're not like eye-gougingly expensive. We have them there. I don't know if Jim has ever used any of them, but we have them available.
Okay, thank you, doctor.
My pleasure.
Dr. Jin, you're still on mute. Please unmute.
Okay, sorry. There's another question here. Do you routinely incubate PRP to 4 degrees? How long? For the low-level laser therapy, is this class 2 or class 4 laser?
I would go 20 minutes or so with the 4 degrees. I mean, you know, that seems to work pretty good. Light therapy for my PRP, is that what the question was? Light therapy for the PRP? Or?
Yes. That's low level.
PRP, we use it 10 minutes, sometimes 20. For stem cells, I only use 20. But again, what I've been using is the Adilite, but within the next few weeks, we'll have something that'll be a quarter of the price of the Adilite.
Okay. Any follow-up question, Dr. Coco? You have any further question? Speak up. Hello? Okay. Anyway, the next question is, how much bone marrow hybrid do you inject? Do you combine it always with PRP and lipoaspirate?
Okay, so my typical case, I have a patient who comes in. I have a patient tomorrow, for instance. I can tell you what I'm going to use. I'm going to take about 5 syringes, 10 cc syringes now with 1 cc of heparin, and I'm going to take about 3 to 4 cc's of bone marrow aspirin in each one of those. Then I'm going to take about 20 cc's of marrow, and then I'm going to centrifuge that down to about 4. So basically, I'm going to put about, you know, 1, 2, 3, 4, about 15 cc's if it's going to be a knee. Now a hip, I can't get as much in. So, but then what else would I use? I'll use about 6 cc's of a fat graft, and I use about 5 cc's of a PRP product. Then I'll put some patches over it.
Okay. So Attorney Vic is here.
My buddy.
Okay.
Yes.
Yeah.
Attorney Vic, how are you, sir?
Yeah, speak up. She's shy. Okay. Yes, Furious. Dr. Furious from Indonesia. Okay. You're raising your hand.
Yes.
Please.
Thank you, Dr. Jim. Thank you, Dr. Purita, for your great lecture. Yes, my question is there any beneficial effect of peripheral magnetic stimulation for combining with the PRP or stem cell or for the regenerative process? Thank you.
Okay, repeat the question. Is there effect of combining PRP with which?
Peripheral magnetic stimulation. Magnetic stimulation.
Peripheral.
Yes,
Yeah.
peripheral magnetic stimulation. Well, let me put it this way. In the United States, a number of years ago, there was a machine very similar. It was called the bionic hair brace. And basically, it's micro stimulation, electrical current, which is very similar. So yes, there is indeed, I had some other slides I could have shown you, but micro electrical current is similar to the magnetic fields, and it does have a beneficial effect on it. So yes, you would not harm the patient by doing that.
Okay, great. Thank you very much.
Dr. Lisa Smigel is here. Dr. Lisa, can you just ask question directly to Dr. Joe? Remember Dr. Lisa, right? Dr. Joe?
Oh, I know Dr. Lisa very well.
Yeah.
Good buddies.
Hi.
Go ahead.
Hi, Joe. How are you? I don't have
Miss Lisa. Good to hear you. That way.
Can you hear me?
Yeah, yeah.
I can hear you.
Okay. So my question is on electroshock therapy. What is the indication? Which problems do you use it for? And if you use it for prior to your PRP or stem cell for its biological effect? And what is the manufacturer or brand that you recommend?
Okay, basically, I think you can use a shockwave on any procedure. It will not, I can't think of a reason why you would not want to use a shockwave. Now, granted, it may hurt a bit, but I think it would help anything because what you're doing, again, you're increasing growth factors, you're releasing growth factors, increasing mitochondria in the stem cells, you're getting endorphins, good things. Now, I happen to use the machine called the Storts. There's another one I think called Smart Wave, which is a lot cheaper. Storts is very expensive. I'm not sure it's worth spending all that money for a Storts. But it does help the shockwave. And I mean, I could see, for instance, on lateral epicondylitis or plantar fasciitis, literally the people feel much better right after the procedure before I put anything in there or anything. So it can help. You know, in the old days, we were using that just to treat lateral epicondylitis and plantar fasciitis, nothing else.
Thank you so much.
My pleasure. I can't hear you, Jim.
You're
You're
on
on
mute.
mute.
Okay, I'm sorry.
Okay, no problem.
Okay. Dr. Joe, a lot of people here are doing PRP a lot of times, and we just would like to guide them as to what kind of an ideal setup would be best for a PRP, because some of them are using 10 cc, 20 cc, some are using 60 cc. So from your point of view, what would be the best, the ideal preparation for a PRP to be considered as a good type of PRP, other than the things that you mentioned about trying to incubate it at 4 degrees and subjecting it to low-level laser therapy? Yeah.
Well, yeah, when we say low-level laser therapy, it should be low-level light therapy. You don't need to use a laser. You can use LEDs, okay? LEDs work very well. Now, as far as how much PRP, well, look, it depends on what you're treating. I mean, if I'm doing a lateral epicondylitis, I'll use maybe 3-4 cc's. If I'm doing a big joint, I'll use 6 or 7. I usually never go above 6 or 7. Now, realize also when I'm treating a joint like a knee or a hip, I'm usually not just doing PRP alone. Remember what I had a slide, angiogenesis versus vasculogenesis. In a joint, PRP is not going to be as good as bone marrow would be because you need SDF1 to really help move things along better. You'll get results from PRP, don't get me wrong, and a lot of you I'm sure have had great results with it, but it'll improve your results if you can use the bone marrow with it. And bone marrow is not that hard to do and really not that expensive when all said and done.
Okay. Pash, you have a question? Go ahead. Pash.
Hi again. So, doctor, you know, we're in physical medicine and rehabilitation, and after a PRP procedure, would it be better, or would there even be any improvement if we were to subject the patient's joint or whatever was injected to a high intensity laser or a low intensity laser treatment after the session?
You know, I think you're using a laser is a good thing. Again, high intensity versus low intensity, you may get some heat there. I think light therapy helps because again, you're going to be increasing mitochondria, and that's the real key here. And you're also going to be doing some transcription of various genes. So I'm in favor of using light therapy. You know, which one, high intensity, low intensity, I'm not sure it makes that big a difference.
Thank you.
Okay, Carmen, you have a question? You can pick up.
Oh, okay, thanks. Hi. Hi, doctor. Yeah, actually, it's a couple of, sorry, this is why I had my audio off.
That's all right. I have
Just
a
a
dog.
question about, a couple of questions. So one is about peptides.
Okay.
What would be your thoughts on oral administration versus injected? Tried to get rid of the
Well, okay, I think it depends a lot of things on your source. Now, first of all, I mean, in the United States, we have some oral peptides. I think BCP 157 and a couple others, and
Yes.
thymosin 4. You know, I use peptides. Basically, those patches I'm talking about are basically peptides. I mean, when all is said and done, peptides are important. They're basically, growth factors are peptides. You just have to have ones that work, though.
Right.
So I'm not sure what your source is, what they are. You got to be a little careful about it. But you know, we use peptides orally also. We're basically giving oral cytokines that we use sublingually, and then we use the peptides. I used to do injectables, but I haven't done it in a long time because I just use the patches. And again, IL-4, excuse me, well, this is my IL-4, interleukin-1 antagonist, interleukin-10, IGF-1. We have basically 3 main patches. One's an anti-inflammatory, one's repair for tendons, et cetera, and then one is basically osteoarthritis.
Okay, thank you.
Okay.
And then the second question was regarding for calcification of joints. What would be your recommendation for dealing with, let's say there's no tendinitis, there is no injury, but there is calcification and restricted range of motion?
Well, do you mean osteoarthritis? When you say calcification, I'm not sure what you mean.
Like calcium deposits into the tissues around the joint.
Well, I mean, a calcium deposit, why would you have calcium in there? Give me an example clinically. I mean, you can get some, I guess you have a hematoma that get calcified, but that's not a common, I mean, to me, when you're talking about calcium, you mean an osteophyte?
Yes.
Well, osteophytes basically osteoarthritis. I just, you know, there's nothing you can really do about them. I just sort of ignore them, and I just, you know, go about my business and inject the joint. Most of the time I'm doing things intra-articularly. Occasionally I'll give some injections, you know, around the joint, but most of the time it's going intra-articularly.
Okay, thank you, doctor.
Okay, Nathan, go ahead with your question. Nathan is from Hawaii.
Oh, that's another buddy of mine.
Yeah.
He comes from,
yeah.
right?
Hello, Nathan. Are you still awake, Nathan?
Nathan, you're still on mute. Please unmute.
Nathan has a question.
Yeah, but he's still on mute, Dr. J.
How's that?
Yeah, Nathan can hear us.
Can you hear me?
Yes, go ahead. Whoa, Nathan, can you sing? Can you sing first? Play a guitar or?
If you guys sing, hey, I miss you guys, everybody. I wanted to say hi, first of all. Dr. Joe, thank you for the great talk. I caught the last part of it. I have a question on the AI patch for an area that's a large area, like say a lumbosacral spine, and you want to put it on a patient. Are you able to just administer the patch in one small area and you'll get the effect throughout a segment of, you know, 4 or 5 vertebrae, or do you have to put multiple patches in across the,
you know, what we're using is we're using 4-inch tegaderm patches, and usually from the AI, you know, from the little container you can do 2 of those patches. So basically, you know, I kind of target where you think the main nidus of pain is, and put one over there and see what happens. Sometimes I use 2, but that, other than that, I don't think I've ever used more than that. But
Okay.
you know, in the midline or something like that. But you can get 2 4-inch patches. That's 8 inches. That's a lot of territory.
Yeah. And you just use the Tegaderm patches for that, right? That's fine.
Works the best. Tegaderm works the best. You don't have to
Okay.
worry, and you leave it on 7 hours, and then it's done. And I've had patients where I gave them in my orthopedic office, I gave them cortisone. This and that didn't work. I tried the patches, worked.
Great.
Okay, great lecture, Dr. Joe. What can I say?
Again, my pleasure.
Such a great lecture. It's like you're learning regenerative medicine in just 2 hours, as I've said. So for those of
What
you,
I'll try and email you the lecture, and then you can pass it on to whoever wants it, okay? Or the guys can just call me directly, whatever works for everybody.
okay, for those of you who may be interested to get the lecture of Dr. Joe, send me your email ad. So as I send it, I'll just send it once for everybody. So everybody gets a copy of that lecture. And we cannot thank you enough, Dr. Joe. It's 10 o'clock in your area, 10:30 in Florida. And I'm pretty sure you're sleepy already, about to go to bed. But thank you for this wonderful lecture that you've shared to us.
Okay, guys, my pleasure and honor. You all take care. Have a good night. A good day, I should say.
Yes, good day. And
All right.
we can see you again, Dr. Joe, soon in Boca Raton. Yeah.
Whenever you want to come, it is an open invitation.
Yeah.
We're here.
So
All right, good.
anyone who would like to learn more about the treatment of Dr. Joe, you can always visit him and email him, and we'll be happy to accommodate you. So thank you again, Dr. Joe. It's a pleasure to have you tonight, and have a good night. And
You too.
Bye for now.
Take care.
Attorney Vic, can you speak? Attorney Vic, are you still here? Attorney Vic, where are
Just
you?
give him my.
Okay, I think he left already. Okay, anyway, he was here. He was listening to you. So thank you
All
again,
right.
Joe.
Much.
And God bless. Yeah. God
Take
bless.
care.
Regards. Yeah. Hello, Desi. How are you? You look beautiful. Very nice to see you all.